0035/20. I will give a brief introduction on gel dosimeter. Dosimeter, in other name for chemical dosimeter and 3D gel dosimeter, are used to analyze using imaging techniques such as MRI, NMR, X-ray CT, or ultrasound scanner. There are two types of gel dosimeter. The first one is spherical gel dosimeter, the second is polymer dosimeter. Both are sensitive to oxygen. So, if there is a presence of oxygen, the oxygen will combine with the hydrogen radicals for spherical gel, and there's a need of antioxidant if there's oxygen inside the polymer dosimeter. This is the working principle of the gel dosimeter for both types of dosimeter. So the first one is the gel dosimeter is defect, and then the dosimeter is filled in the anatomic printer, and then dosimeter is in as a clinical, and then it will irradiate gel dosimeter and analyze an MMR, and then NMR images of a phantom is obtained. Absorbed dose is calculated from the NMR images. Types of chemical dosimeter. There are three types. The first one is spherical gel dosimeter. The second one is polyacrylamide gel dosimeter (PAG). The third one is polymethacrylic acid gel dosimeter (MAG). Gel dosimeter have a range of a dosage of 5 to 400 gray, and the dose rate is up to 106 gray per second. 96%, it has 96% of water content, and hydroxyl radicals are generated after irradiation. In the image on the top shows that the equation of formulas that after the irradiation occurs in the spherical gel dosimeter. After the irradiation, the iron 2 ions is converted into iron 3 ions while emitting an electron. Where iron 2 ions is ferrous ion, iron 3 ions is called ferric ion. There's a change of +2 to +3. The change of this +2 to +3 will change in the paramagnetic properties. Imaging techniques are such as NMR and MRI. 3D images with high spatial resolutions, dose distribution created. Absorbed dose after irradiation is inversely proportional to the T1 of the gel in MRI. This is the receipt for the preparation of the gel. So they need 1.5 millimole of ferrous ammonium sulfate, 1 millimole of sodium chloride, 30 millimole of sulfuric acid, and gelling agents, chelating agents. So in this dosimeter, spherical gel dosimeter, there are some problems faced, such as instability of the gel with time, as the limited of diffusion of ferric ions through the gel matrix, low sensitivity of the gel dosimeter, variable response of the dosimeter, decreased system sensitivity when oxygen present in the solution is depleted, blur dose distribution produced if continual irradiation, diffusion of ions, and high sensitivity to impurities. Next one is the PAG, polyacrylamide gel dosimeter. It's a type of polymer dosimeter which is widely used as a 3D gel dosimeter. Acrylamide is a dangerous neuron toxin. It is suspected human carcinogen that require careful handling. Fewer problems with dosage and temperature sensitivity, and can be detected using several imaging techniques such as MRI, optical CT, X-ray CT, and ultrasound scans. On the figure above, it shows that some of the polymer substance that can be used as a polyachromatic gel dosimeter PAG. In this slide shows the receipt of a PAG which contains of water and gelatin. It also contains of monomers and cross-linkers that dissolve in the gelatin matrix. NIPAM, DAA and NVF are used as they are similar chemical structure to acrylamide and less toxic than acrylamide. They have a good water solubility and not expensive for clinical use. The full name is as the table I've shown in the slides. After irradiation for the PAG, the free radicals is generated by the water radiolysis. Water number of cross-linked polymers particles forms precipitate of the gel depends on the dose, radiation dose, and concentration of the monomers and cross-linkers. There's a change in the physical properties after irradiation in PAG as well. In this PAG, there's some problem faced, which is inaccurate dosimetry results, where polymer radicals keep on producing over a long period of time and unable to react with the diffusing monomers and cross-linkers. The next one is the MAG, polymetacrylic acid gel dosimeter, which is also known as normal SIG dosimeter, which is prepared under the normal atmospheric condition that exclude oxygen. MAG consists of metallic acid, gelatin, water, and small amount of other agents such as THPC or other oxygen scavengers. Oxygen scavengers can act as antioxidants to prevent inhibition of polymerization by oxygen. So after irradiation, free radicals polymerization produced during radiolysis of water. Polymer precipitate is held in place by gelatin, depends on the absorbed radiation dose. It can be detected using MRI, X-ray, CT and other imaging techniques. It does not require the aid of cross-linkers as it contains metacrylic acid monomers. And these are my references I have used for both introduction and the working principle, and as well as the type of gel dosimeter. Thank you.
Hi, my name is Shafiq. So, there's several properties of the gel dosimetry. The number one is the dose response and operating dose range. So, in this graph, it's shown that the dose response curve with the gel 6% T and 50% C, which is an A and B is displayed as A is a high dose and the B is displayed as a low dose in duration. So in the dose with the R2, which is this one, is the it's not linear. This one, sorry, it's not linear with this one. So, but it is well represented as a bi-exponential function, which is the low region of dose R2 curve is shown in the 2B. This one, it's clear that this is region have a dose as a low sensitivity compared to this one. And then dose R2 can be well approximated by linear plot within the dose area. And then dosimetry are commonly used in the clinical dosimetry for radiation, subject as a treatment and a fairly accumulative dose radiation. The distribution dosage is proportionally scaled by the same dose as level as the medication. The number two properties is a time dependence on the dose response radiation. So we usually use this Arrhenius relation. So the dose which is K equal to A dot E exponential EA over KT. So the dose R2 response is determined by the overall radiation induction in polymerization reaction rate, which is can be depend on several constants. either be that the viscosity and the temperature also have contribute to the major effect of a dose response. Like example, we can observe a temperature at 28 degree. It should be like, remember that gel is a liquid at that temperature. With the high sensitivity in observation, can be seen that the MAG or normacic metacrylic acid for the radiation temperature, observe that the no gel sol will be observed at the 30 degree Celsius in the case of this particular polymer in the gel dosimetry. And the number 2 is the temperature dependence of the dose response upon scanning. Upon scanning, the temperature is also contributed to make a dose response. So inside they have a dipole-dipole interaction. Could be less if the movement of the water molecules and monomer and polymer structure in the solution increase with the temperature. As a result, increase the temperature, the R2 polymer would decrease, and the temperature can also affect the magnetization transfer and the chemical exchange of the proton. So the temperature dependency is rather proportional to the dose sensitivity. So higher the dose, higher the dose sensitivity. This is not an expected outcome, as a dose sensitivity of the two gel dosimeter is resolved by the different mechanism. And the number 4 is a dose integrity. So in the polymer gel dosimeter, another process can occur that is responsible for possibility dose overshot, which is nearly step to dose gradient in combination with high dose. The polymerization reaction that occurs in the gel at particular location is depend on the amount of monomer that is accessible at that particular location. It is understood that the study of temporal stability that polymerization persists for many hours are irradiated. So for the next flush, which is the fresh monomer, would from the lower dose region to the higher dose region occurring during this time. Number 5 is a dose rate dependency. So the equilibrium concentration of the water radicals present during the radiation in pure water is highly dependent on the rate of dose. So termination reaction determines the concentration of water radicals in water and is represented by the different equation, like this one equation. Okay, so the reaction rate constant for the termination reaction of radical is kT, and the yield of the constants for the yield of the constant and the yield for the constant for radical formation in a proton beam. Okay, like this one, kg dot g is the dose, this rate of doses, and the equation above is a Raketti type, which is a differential equation that can be easily solved by substituting the solution. Okay, if you want to use this equation, we need to substitute like what type of polymer that we use to determine the concentration of water radical in the gel dosimetry. Okay, the number 6 is energy dependency. So the relative fraction of interaction process is well known to the base of the form of the radiation. In the different relativization fraction of interaction process, different photon energy will result. So the different fraction of a water radiolytic products may result from this. Another dose response may be predicted, as the reaction rates of monomers with different water radiolytic products can be different. So the number 7 is a tissue equivalent. The equivalent between the dose measured and the dose absorbed by the patient tissue is another important parameter of the dose for the clinical application. So this parameter, also referred as a tissue equivalent, can be measured using the proton and electron cross-section from the various chemical elements found in the gel dosimetry by Monte Carlo measurement and the depth dose curve. it has been shown that the electron density of the dominant factor determined by the water equivalent of the gel dosimeter. The mass density of the electron density of the PEAG and the MAG dosimeter can be shown to be significantly higher than the water and very similar to the muscle. The density need to be reduced to achieve the lung equivalent gel dosimeter. This can be done by addition of beads filled with the gas and forming the gel during the processing. The low MR signal diffuse attenuation MR signal causes a microscopic magnetic gradient resulting from the susceptibility varies between the gel and the gel are the major challenge of the lung equivalent. So this one is for MRI. We can be used. Okay. This one with the lower MR signal and the diffuse attenuation of the MR signal can caused by the microscopic magnetic field resulting from the susceptibility varies between the gel. That's all for me. Thank you very much.
In this part, we will discuss the clinical applications for the three-dimensional dosimeters, which can be used in clinical practice in radiation oncology. To be specific, it is used for evaluation of new tools and radiation delivery techniques. It's also being used as an external QA addition tool to monitor the quality of dose delivery. In the next figure, we will present a standard measurement and analysis procedure when we use the three-dimensional dosimeter for evaluation of the delivered dose. In this figure, we are showing the process which is used the three-dimensional dosimeters like magnetic resonance imaging, MRI, OCT, which is the optical computer tomography, XCT, which is the X-ray computed tomography. Examples for three-dimensional dosimetry. Bank series produced and sold by three-dimensional dosimetry company, which recently produced the RGD dosimetry as a crystal ball. Another company like his company, which is owned by Dr. Adamovic, produced the most common imaging device for the dose quantification of PGD and FGD is the MRI system, magnetic resonance imaging system, and it is readily available at the most facilities. But there are just two companies which supply OCT systems for PGD, FGD, and SPD. The three dosimetry company, which sells its Octopus series system, which is in London and Canada, manufactures two types of cone beam based OCT system, which is named as Vista. The analysis software should be able to process the raw image data acquired by the imaging device and convert the raw data to the three-dimensional dose. Also, it is desirable for the software to be able to perform the evaluation of the measured dose in comparison to the reference data from TPS, Monte Carlo code, or other three-dimensional dose measurement tools. But the gamma index analysis capability, in addition to volumetric analysis such as generation of dose volume histograms DHV using the contour data from TPS, is the desired function. The commercial OCT system, Octopus and Vista, come with the analysis software. Most research groups in this field developed own data analysis software, thus cannot be used for the work directly related to routine patient treatment, but are excellent tools for research related to new equipment and delivery techniques. This can be easily available for free from the developers. The regular quality assurance (QA) involves the measurement of beam output and the evaluation of the mechanical and dosimetric accuracy. Other regular quality assurance includes the dosimetric validation of the treatment plans for every IMRT and VMAT treatment. Also, dosimetric measurements performed at the equation of the new accelerator or the annual quality assurance can be included in this category. The three-dimensional dosimeters are not used for this purpose currently. In order to reduce the rate of error in dealing with patients, radiation measurement tools must be examined before they are used in measuring the ray that the patient is exposed to. And this is what is done when pseudo three-dimensional dosimetry tools are being introduced into clinics for routine applications. The device must be tested and its accuracy must be evaluated before actual applications for patients. PGD, FGD, and SPD are ideal tools for such evaluation studies. One example in this area is assessment of the ARCHIC device, Sunny Nuclear in Melbourne, United States. This device, the results demonstrate a satisfactory agreement between these two measurement techniques, hence confirming the measurement accuracy of the new device as a pseudo three-dimensional dosimeter. This application of PGD is a critical step to demonstrate its value and suggests that the PGD should be invaluable. PGD may become the standard tool for evaluation and pseudo three-dimensional dosimeters which will be developed in the future. End-to-end quality assurance. This test can be accomplished the most adequately by using the three-dimensional dosimeter because the shape of patient can be simulated easily by using these tools. The earliest application of PGD was made to the end-to-end quality assurance of gamma knife stereotactic radiosurgery. One of these studies could in fact point out a non-negligible geometric error associated with the image, which was not considered or quantified before. As a matter of fact, all of the MRI-based PGD or GKSRS is considered as an end-to-end test of the dose delivered when the dose delivery is planned on the MRI, which was taken before planning and radiation delivery. Applications of three-dimensional dosimeters to other types of SRS technique have not been performed as often as gamma knife stereotactic radiosurgery for an unknown reason. The dose delivery technique of IMRT and VMAT, including tomography, requires very sophisticated mechanical maneuver of the MLC, jaws, and the angles of gantry and collimator. The radiation delivery is in essence four-dimensional because of the positions of all these components move during a single delivery of treatment. Hence, the precision of delivering dose is affected by the composite of many factors. An individual test of this element is not sufficient. Hence, the actual three-dimensional dose evaluated of these technologies should be performed at least once before the introduction to clinical usages. The three-dimensional dosimetry tools can be used effectively for this purpose. The major goals of the three-dimensional dosimetry is the validation of the three-dimensional dose distribution predicted by TPS by comparing with the measured dose with reflex and performance of the radiation delivery system. There are many studies of this topic.
Hi everyone, my name is Khalila. I will explain about the advantage and disadvantage of gel dosimetry. First of all, I will explain about the advantage of gel dosimetry. According to the M. Khan et al. 2019, the advantage of the gel dosimetry is a tissue equilibrium. Thus, it does not disturb the fluency and spatial distribution of ionizing radiation. Besides, the dose distribution can be read out by the 3D technique within one scanning procedure, and the 3D dose representation might be calculated quickly. According to the Kumar and Seymour 2010, this dosimeter also acts both as a phantom and detector, thus confirming the versatility of the dosimetry technique. Next, according to Ethic et al. 2017, the disadvantages of gel dosimetry include the usage limitation, the dosimeter due to the diffusion problem. The introduction of polymer gel solved the diffusion problem of the Frinker gel. So, the polymer gel are more advantageous than the Frinker gel because of their non-diffusion property and stability. However, the polymer gel may be affected by the concentration of cross-linkers and the oxygen contamination. According to Baldock et al. 2010, the gel dosimeter requires the complete preparation and evaluation. Frinker gel are more sensitive to the conditions such as impurities and temperature during preparation, irradiation, and the layout. During the preparation of the polymer gel, proper safety precaution is needed. For example, prepare the gel dosimeter in a fume holes and using the glove, goggles need to be used. The gel dosimeter does not directly give the measurement. However, it needs the evaluation by the MRI. Furthermore, the gel dosimetry has a high cost, which the total cost of the gel dosimetry system in the 5 year for the regular patient specific IMRT or VMAT quality assurance is 13,000. Meanwhile, the cost of the R-check system is only 5,000. Hence, there is a considerable disadvantage of the gel dosimetry over the R-check regarding the cost. According to Wanabel et al. 2017, the development of reused gel dosimetry can lead to significant cost saving. Besides, the next consideration is about availability of the analysis software to process the raw data to the 3D dose distribution. Most research groups in the gel dosimetry field develop their own data analysis software. However, the analysis software cannot be used for the routine patient treatment quality assurance, but are excellent tools for the research related to the new equipment and delivery technique. Okay, this is a several reference that I use for finishing this part. Thank you.